Hello and welcome back to your organic chemistry. In this little video we're going to look at how we name compounds, and that's nomenclature, which basically means naming organic molecules, and we've done this already with our alkanes, halogenoalkanes, alkenes and alcohols using the IUPAC nomenclature, naming molecules. In the next video we're going to look at isomerism, but we're going to focus in this video on nomenclature. So this is your A-level independent study booklet. You will have a PDF copy of this. You'll be given a hard copy when you come back to college. So as usual, on the first page of your booklet, you're asked to identify some of the functional groups in some well-known drugs like cocaine, morphine, heroin and LSD. And what you're asked to do is to circle and label as many functional groups as you can. And you can't do this until you can recognise the different functional groups. So what I'm going to do before we even try naming or identifying these functional groups is first of all look at some of the functional groups that we've already met at AS, and also some of the ones that you're going to study at A-level. And then at the end of the video we'll come back to circling these functional groups and recognising them. That we're going to focus on is this section here with a list or a nice table or a summary of all of the functional groups. The only ones that are missing that you might encounter are the ethers, and we don't study the chemistry of the ethers because they're quite unreactive, but you might come across the ether functional group. So the functional groups that you've got to recognise are listed here in this second column. So the ether functional group is when you have a carbon that is joined to another carbon by an oxygen, and we don't study the chemistry because they're not very reactive. So we're not going to bother looking at how to name ethers. And the other functional group that is missing are the arenes, or the aromatic groups, which you will recognise either with a six-membered ring, either with a circle on it, or with what we call the Kekulé structure with 3 double bonds. And we're going to come to the arenes later on and how to name arenes in the aromatic section. So if you just add these to the table, and we'll look at how to name them later on. Before you can learn to name organic molecules, you first of all have to recognise the functional groups, and some of these will be familiar to you already. So first of all, let's have a quick recap on our halogenoalkanes. Halogenoalkanes is an alkane skeleton with either carbon, with a chlorine, a bromine or an iodine atom attached to the carbon skeleton. So that halogen group there could either be a fluorine, a chlorine atom, a bromine atom or an iodine atom. The next group of molecules we looked at in more detail were the alkenes, and the alkenes can be characterised by a carbon double bond carbon. As the suffix suggests, -ene, whenever you see the suffix -ene, you know it contains a carbon double bond carbon. You also went into some form of isomerism, which we will touch on later, but needless to say, an example would be ethene, and eth suggests that the stem has got 2 carbon atoms, and ene suggests it possesses a double bond. So ethene would quite simply be a carbon double bond carbon with 2 carbon atoms. Here notice we've got what's called a crab notation if you try and keep your bond angles at 120 degrees around the structure. In the next part of your organic chemistry, you went to look at the alcohols, and the alcohol is simply like an organic derivative of water, whereas instead of having another hydrogen here, as you would in water, we have a carbon atom attached. So the most common alcohol that you come across on a day-to-day basis is ethanol. So ethanol, as the stem suggests, is eth, contains 2 carbons, and because it's got the suffix -ol, that suggests it's got a hydroxy group or hydroxyl group, which is the OH. and there's the carbon, the rest of the carbon skeleton. So an alcohol is characterised with the OH functional group. Following on from the alcohols, we now move on to the A-level chemistry. And when you were looking at alcohols, we looked at the mild oxidation of alcohols. So you've already met aldehydes. Aldehydes are characterised by a carbon double bond oxygen joined to a hydrogen atom here. First of all, the name of an aldehyde is characterised by the suffix -al. So let's look at a simple aldehyde, ethanal. Again, the stem eth suggests it's got 2 carbon atoms, and al, the suffix al, suggests it's got a carbon double bond oxygen and a hydrogen atom. So there is ethanal and aldehyde. So this group here that we're going to come across a lot, the carbonyl group, is common to our next molecules. Very similar in structure to the aldehydes are the ketones. And if we look at the ketone as compared to the aldehyde, the ketone functional group also has the C double bond O, the carbonyl, which is characterised by a C double bond O. However, this time the carbon isn't attached to a hydrogen, it's attached to another carbon. And you came across ketones when you looked at the mild oxidation of secondary alcohols. So let's look at a typical ketone, propanone. Its old name acetone that you use to remove nail polish. And ketones can be characterised by the fact this double bond O, one, ketone, is in the middle of 2 carbons. Prop is the stem, 1, 2, 3, prop, and therefore the double bond oxygen has to be on the carbon that's on the middle, and there's the rest of the hydrogen atoms attached. So that is propanone, a ketone. Now if we look at the other molecules that are related to, that contain the carbonyl group, they're carboxylic acids, esters, acyl chlorides, acid anhydrides and amides. These group of compounds, this family of compounds, are called carboxylic acid derivatives because carboxylic acids possess the carbonyl group and soda esters, soda acyl chlorides, soda acid anhydrides and soda amides. So we'll look at these compounds in turn as carboxylic acid derivatives. First of all, let's zoom in on carboxylic acids. Carboxylic acids you've already come across from the vigorous oxidation of primary alcohols. And a carboxylic acid contains 2 functional groups on the same carbon. It contains the carbonyl group that you can see here, and it also contains an OH group exactly the same as there is in alcohols. So the carboxylic acid that's present in vinegar, ethanoic acid, the suffix oic suggests it contains a carboxylic acid group, oic acid, and the stem ethan suggests it contains 2 carbon atoms. So ethanoic acid contains the carboxylic acid group and the eth stem of 2 carbons. So that is ethanoic acid. Now, when we come to look at esters, esters are in fact a carboxylic acid joined to an alcohol. And therefore to name esters, so if we look at a typical ester would be something like methyl ethanoate. So this suffix -ate suggests it contains this carbon double bond oxygen group. The methyl part in methyl ethanoate is from the alcohol, which will be this part here. The ethanoate or ethanoate part comes from your carboxylic acid. So this ester, methyl ethanoate, first of all, would have a methyl group from methanol. And the second part, the ethanoate, comes from ethanoic acid, which would be C double bond O, and the suffix O8, and ethan, the stem, it's got 2 carbons, methyl ethanoate. When we come to look at the acyl chlorides, again the acyl chloride is an organic derivative of a carboxylic acid. However, in place of the OH group, we have a chlorine atom here. So let's look at a typical acyl chloride, for example, propanoyl chloride. So whenever you see the suffix oil, it suggests it's an acyl chloride. Propan suggests that the stem is 3 carbons, 1, 2, 3. Oil contains a C double bond O with a Cl on the same carbon, and then we quite simply add the hydrogen atoms. So that is a carboxylic acid derivative. If we now look at the carboxylic acid derivatives so far, we have carboxylic acids with C double bond O OH. Ester, the OH has been replaced by an alcohol group. In acyl chlorides, the OH in the carboxylic acid has been replaced with a chlorine. Now let's look at the acid anhydrides. So the acid anhydrides are in fact 2 carboxylic acids joined together with the loss of water. So let's see how this works. So if we look at a acid anhydride that you're going to make aspirin with, so that's ethanoic anhydride, that tells me that 2 molecules of ethanoic acid have had water removed to make ethanoic anhydride. So let's have a look at that. So here's 1 molecule of ethanoic acid, CH3, C double bond O, OH. And if we draw another molecule of ethanoic acid underneath it, CH3, C double bond O, OH. And we remove a molecule of water, we are then left with ethanoic anhydride, CH3, C double bond O, O, C double bond O, CH3. So that is ethanoic anhydride. So anhydrides are characterised by 2 carboxylic acids joined together with an oxygen. The final group of carboxylic acid derivatives are the amides. So let's look at a typical amide. Let's look at propanamide, propanamide, and as this suggests, propan suggests that it's got 3 carbon atoms, 1, 2, 3. The amide group is a C double bond O, N. Now this is called a typical amide, an unsubstituted amide. So this is propanamide, but say you get something like N-methyl propanamide. This is called an N-substituted amide, and it means that one of these hydrogen atoms here has been substituted by an alkyl group. In this case, it's a methyl group. So N-methyl propanamide would be exactly the same structure. However, this hydrogen here will have been replaced by a methyl group. So that's an N substituted amide. So far we've looked at the derivatives of carboxylic acids. So that's esters, acyl chlorides, acid anhydrides and amides. And the final two functional groups that we're going to be studying at A level are the amines and the arenes. And if we first of all look at the amines, amines are also known as organic derivatives of ammonia. So we can see here that ammonia would normally be a nitrogen with 3 hydrogen atoms, and here one or more of the hydrogen atoms can be substituted with an organic group like an alkyl group. So let's just replace one of these hydrogen atoms with a methyl group. So that's just like ammonia, but we've replaced it with a methyl group, and that would simply be called methylamine. Now we can replace more than one, and I'm not going to go into too much detail here. So let's replace two of the hydrogen atoms with methyl groups. And when you looked at nucleophilic substitution of halogenoalkanes with ammonia, you've already met this multiple substitution. And this one here is called a secondary amine. So this one would be dimethylamine. Let's look at another example, this time with 3 carbon atoms, but with the amine group coming off carbon number 2. So this is still a primary amine because only one of the hydrogens has been substituted. So that would be called, in this case, 2-aminopropane. So when the amine group is other than on position 1, you can refer to the amine group with the prefix amino. And again, when we study amines, we're going to go into this in a lot more detail. Finally, looking at our functional groups are the aromatic compounds, or the arenes. So the ene suggests it's unsaturated like alkenes, but we have got this what we call a benzene, and we call this a benzene ring, and you'll sometimes see the ring drawn as if it has 3 double bonds. So in some textbooks it's convenient to see that ring drawn as 3 double bonds, and depending on where the benzene ring is in the molecule is how you would name it. So let's look at a typical simple molecule. Let's look at a ethane with a benzene ring attached. So there's ethane with a benzene ring substituting one of the hydrogens. So in this case that would be called ethyl benzene. So the benzene group is this, and we treat the ethyl group as a substituent on the benzene ring. So that would be ethyl benzene. If, however, the priority group is, for example, here we've got the amine group as the priority group, the arene or the benzene side chain is referred to as a phenyl group. So this would be phenylamine. And again, when we come to study benzene and aromatic compounds, we'll go into much more detail of how to name compounds. So just to recognise that this is a benzene ring and it can be referred to as a phenyl group. So these questions here have come from your independent study pack for nomenclature. And what we're going to do is systematically try to draw these structures here. So what we first of all do is let's identify which of the functional groups, which of these families they come from. So if we first of all look at A, bromoethane, bromo suggests it's a halogenoalkane. Propanoic acid suggests it must be a carboxylic acid because it ends in oic acid. Propanal suggests it's an aldehyde because it has the suffix al. Butantuone suggests it's a ketone because it's got the suffix -one. Methyl ethanoate or ethanoate suggests it's an ester because it's got the suffix -08. 2-chloropropane, chlorine is a halogen and therefore it must belong to the halogenoalkanes. 4-methyl nitrobenzene suggests it's an arene because it has the suffix benzene in it. Pentuene suggests it's an alkene because it possesses the suffix -ene and therefore it must have a carbon double bond carbon in there. Butanol suggests it must be an alcohol because it's got the OH suffix, ol, alcohol. Similarly to methylpropan2-ol, it has the suffix ol, so it must be an alcohol. But-1,3-diene suggests it's an alkene because it has the suffix -ene. 2-amino-2-phenyl-ethanoic acid looks complicated. However, if we break it down, this prefix amino suggests it must contain an amine group. Phenyl suggests it must contain a benzene ring, and oic acid suggests it must contain a carboxylic acid group. So more common organic molecules in everyday life don't just have one functional group, they have more than one functional group. But we can be systematic in drawing the structures, and what we're going to do is we won't draw the simpler structures, you can do those yourselves. We'll choose some of the more complicated structures. 2-methyl-amino-methane. Amino suggests it contains the amine functional group. Similarly, methanoic ethanoic anhydride. The suffix anhydride means it has to be an acid anhydride. Butanoyl chloride, oil chloride, acyl chlorides have the suffix oil, so it must be an acyl chloride. Ethyl methanoate suggests the suffix is -08, so it has to be an ester. So what I suggest is you copy out this table, not a table, this diagram here, and write down the names of the prefix or suffix of the compounds, and then you can quite simply recognise them. And the more of these you do, the more your brain memory will remember each of these functional groups. So let's do this one here. N, 2-amino-2-phenyl ethanoic acid. And what we're going to go for is the ethanoic acid and work backwards. So we know that ethanoic acid has 2 carbon atoms because the stem is eth. Ethanoic acid is a carboxylic acid, so it's C double bond O and an OH. So there's our ethanoic acid bit. And if we consider that is carbon number 1 because it's got the main functional group, on carbon 2 we have an amino group, and we know that comes from the amines, so that is NH2. And it also has a phenyl group on carbon number 2, and the phenyl group we know is the benzene ring. And then we need to make sure that every carbon now has got the correct number of bonds. So this carbon here has got 1, 2, 3, 4 bonds. This one's got 1, 2, so we need to now put a hydrogen onto there. So that is our 2-amino, 2-phenyl ethanoic acid. What we're going to do now is let's draw a more, again, one of these more complicated structures. How about N-methyl amino methane? N-methyl amino methane. Well, we know that methane has got 1 carbon. So let's start with methane. Amino suggests it's got an amine group. Now the N here suggests that on the nitrogen we have got another methane group. So let's take off one of the hydrogens and let's put on another methyl group. So this could have 2 names. This could be N-methyl aminomethane or simply dimethyl amine. Let's now look at P, which is methanoic, ethanoic anhydride. Methanoic, ethanoic anhydride. So remember we said that anhydrides were 2 carboxylic acids with water removed. So here is ethanoic acid, and here is methanoic acid, and notice I'm drawing the OHs next to each other. Anhydride suggests water's been removed, so if we take a molecule of water away, then methanoic anhydride would simply have the structure C double bond O from your ethanoic acid, and from your methanoic acid C double bond O H. In this next exercise, what you have to do is to name the structure from given a condensed formula. And as it correctly suggests here, it says draw the full structure before attempting to name the molecule. So we're going to do the simplest one. We'll do A first, which is CH3Br. So if we draw the structure out, CH3Br, immediately you can see that it must belong to the halogenoalkanes because it's got a bromine atom there. And also you can see that the stem is going to be a meth. Why? Because it's only got 1 carbon. And therefore it would make sense to name this molecule bromomethane. You don't need to give the position of the bromo group because there's only 1 carbon. So that's bromomethane. Now let's look at B. This is an interesting one because it's got C6H5. And whenever you see C6 and with a low number of hydrogens, immediately that's got to be a benzene ring. So whenever you see C6H5, it must be a benzene ring. So let's draw the benzene ring out first of all. Sometimes this takes practice. So I do a little house with a little bit underneath there. And it's got a chlorine. It's not given the position of the chlorine. It doesn't matter because there's only 1 there. And therefore, we can simply name this as chloroethane. chlorobenzene. C is a little bit more difficult, and again, if we draw out the carbon skeleton, so the carbon skeleton has got 1, 2, 3, 4 carbon atoms. So let's draw out those 4 carbon atoms. 1, 2, 3, 4. On carbon number 1, there's a CH3. Carbon number 2 is CH2. Carbon number 3 is CH, and in brackets OH, so that just means that the OH goes on to here, and then a CH3. And now it's a lot easier to see how to name this once we've drawn the full displayed or graphical formula of the molecule. So this is 1, 2, 3. So on carbon number 2 is an OH, and we know OHs are alcohols which have the suffix -ol, and therefore the name of this molecule, bute, because it's got 4 carbons, so the stem is bute, butan. We leave off the E because the suffix is -ol, which is a vowel. If it was a consonant, then we would leave the E on. So it's butan 2-ol, because the OH group is on position 2. Let's now look at D. And D has got 2 carbons. And whenever you see COOH or COO, recognize that as a carboxylic acid. So what you can do on your little chart here is to simplify that with the condensed formula as a COO. It's got 2 carbons, and therefore its stem is eth, and it's a carboxylic acid, so that is ethanoic acid. The next molecule along here, E, contains a CHO. I call that a CHO group, and a CHO is an aldehyde. So when you've drawn out your chart of functional groups, the condensed formula for an aldehyde is a CHO. If we draw out the carbon chain, it's got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 with a CHO. I'm not going to put all the hydrogens on to save time. And therefore the stem for 6 is hex, so that's hexane, and the suffix for an aldehyde is al. We don't need to give the position because it will always be on the end carbon, carbon number 1. F, again, when you draw the full structure out, has got 2 carbon atoms with a nitrogen on the end. And we know that if it's got a nitrogen, it's an amine, and it's got 2 carbons, and the stem is ethyl, because ethyl is the alkyl group that's attached to the amine, ethyl amine. H is obviously a halogenoalkane, and if we draw it out, we have a bromine atom on carbon 1 and a bromine atom on carbon 2. And therefore, that is 1, 2, because the bromine atoms are on position 1 and position 2. There are 2 bromines, so dash dibromo ethane, stem ethane, because there are 2 carbon atoms. Whereas if we look at I, both the bromine atoms are on carbon number 1. So that would be 1, 1, dibromo ethane. Last time I missed out G, so if we look at G, it's got a CO, and when you see a CO, we know it's a ketone. It's got 3 carbons, and the CO will go in the middle there. I'm not putting the hydrogens on. The stem is prop because it's got 3 carbons, propan, and the suffix -one because it's a ketone. Now let's look at J. It's got a double bond. Now whenever you see a double bond in a molecule, can you get into the habit of using what's called the crab notation and putting all of your groups around this main skeleton here? So let's start with this end here. So that's a CH2. We've got rid of that. We've got an H. And here we've got a CH3, CH2. So that is 1, 2, 3, 4. So it's a bute. And the double bond is between carbon 1 and carbon 2. So it's bute 1-ene. K, again here we see the C6H5, which we know is the benzene group. So it's got a benzene ring and it's got a Cu, which is a carboxylic acid. So if we now put that on there, C double bond O, OH. Now this can have a few names. The common name for it is benzene carboxylic acid or benzoic acid. And the naming of aromatic compounds can vary, and when we come to look at that topic we'll go into that in more detail. Let's now have a look at L, and you can see it's got a COOC, and a COOC is an ester. I call them kooks. So aldehydes were CHOs, ketones were COs, carboxylic acids are COOs, esters kook. And if we draw out the full structure of the ester in L, again when you see an ester, draw the functional group skeleton first, so it's a C double bond O, O, and then put the rest of the molecule around it. So on this side it's O, CH2, CH3. And this part here comes from the alcohol, so that's the alkyl part of the ester. Here it's CH3, CH2, C double bond O, so CH3, CH2, C double bond O. And this bit is the O8 part, the bit that's come from the carboxylic acid. So the stem of this is 2, so that would be ethyl, and this part here has got 3 carbons, so that would be propanoate, and it's an ester, ethyl propanoate. M, as you can see here, has got a carbon oxygen chlorine. Carbon oxygen chlorine, I call those cockles, acyl chlorides. And so again, draw out the structure of the functional group first and then put the rest of the molecule around it. So here you can see it's got 1, 2, 3 carbons here. So the longest chain is 4, so the stem is bute. It's an acyl chloride and we know that they end in oil chloride. So it's butan, oil, no E there because this is a vowel, butanoyl chloride. Let's now go to this thing here. Can you see this brackets and 2? And that suggests to me that that is an acid anhydride. And if we draw the structure out, you can see it's got 1, 2, 3, 4 carbon atoms. 1, 2, 3, 4 carbon atoms. And because it's an anhydride, it's going to be a double bond O, O. And then the other part that's also in the bracket is also got 4 carbons, like so. I'm not going to put the hydrogens on. So because it's 4 carbons, the stem is bute. So that is butanoic anhydride. 2 molecules of butanoic acid with a molecule of water removed. Butanoic anhydride. Look at O, and oops, I rubbed it out. And again, we can see here that it contains a C double bond OC. So we know it's an ester. So we start off with drawing the skeletal structure of an ester and then working around it. So before the CO, there was a CH3, which we'll put that on now. And then following the O, there's a CH2, 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 CH3, CH2, 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 CH3. And now, remember it's made up of 2 parts. The part that comes from the alcohol, here the alkyl group, has got 4 carbons, so that's butyl. The part that comes from the carboxylic acid here has got 2 carbons, and therefore that's come from ethanoic acid, so that's butyl ethanoate. Let's now look at this molecule here. It's a COC, which suggests a COC, which we know is a ketone. So again, we'll draw the C double bond OC first with 2 carbons around it. And before the CO is 1, 2, 3 carbon atoms, and on the other side of it is 2 carbon atoms. If we number the chain, 1, 2, 3, 4, 5, 6, it's definitely a hex, and the lowest number position, if we go the other way, 1, 2, 3, 4, the carbonyl group is on position 3. So this is hexan, again no E because it's followed by a vowel, so that's hexan 3-one. Let's now go to Q. Again, it's an alkene, so it's got a double bond in. Let's start off with the crab notation, C double bond C, and then we can put all of the atoms around it. So on the left hand side of the double bond, we've got a CH3, CH2, and then a CH. So CH3, CH2, and then there's our CH. And on the other side of the double bond, we've got an interesting scenario here. We've got a CH, which is the carbon that's joined to there. And then on the other side, we've got a carbon, a hydrogen, but in brackets, we've got 2 CH3 groups. So this is an interesting one. So let's now look for the longest chain. I'll number them. So it's either 1, 2, 3, 4, 5, 6, or going the other way is 1, 2, 3, 4, 5, 6. This molecule has a methyl group side chain, so that could either be on position 5 or it could be on position 2, so we'll give it the lowest number. So it has a methyl group and it has a double bond which is on position 3 or 4, so we put it on position 3. So this molecule has got 6 carbons altogether, so its stem is hex, and therefore we're going to name it 2-methyl hex 3-ene. I is one we've not come across, it's not on this cycle here, so I'm just going to put it in. Whenever you see a C triple bond N or N, That's a nitrile. We have come across nitriles when we did halogenoalkanes. It's not on our circle. So let's look at the structure of a nitrile. So that's C, C, and when you see a CN, can you put in the triple bond N? This is called propane, and we put the E in because it's followed by a consonant, nitrile. We don't need the position because it's on position 1. And again, you can put your hydrogens around that molecule there. And finally, S. So let's draw the structure out. It's got 4 carbon atoms. 1, 2, 3, 4. One of them is a nitrile group, and we've also got an OH. Now, when you've got a nitrile group, the nitrile group takes priority over the OH. So it's got 4 carbons. So this is going to be 2 hydroxy butane. Let's rub that out. 2 hydroxy, because it's got 4 carbons. 1, 2, 3, 4. 2 hydroxy butane nitrile. So it looks like it could be an alcohol or a nitrile. And the priority group is the nitrile. So when an OH group is a branch, we give it the prefix hydroxy. So now let's get on with the fun bit of circling and recognising these functional groups and seeing how many you can get yourself. So if I use my little highlighter here, immediately there's my C double bond OO and a C double bond OO, and we can recognise those as ester groups. Here is a 6-membered ring, and therefore that thing there is a benzene ring. I'm just going to go back to this. So there's a benzene ring. Here we have a nitrogen, and the nitrogen is connected to 3 other carbons. So that is a tertiary amine. Let's now move on to morphine. And we can see here again is a nitrogen connected to 3 other groups, and that is a tertiary amine. And we can see there is a carbon double bond carbon there, so that's an alkene. We have a 6-membered ring. Now, a 6-membered ring we can classify as benzene, but when we have a benzene ring and an OH, it's not on the AQA syllabus, but when you have a benzene ring with an OH attached, we call that a phenol. But if you said that was a benzene ring and that was an alcohol, that is perfectly acceptable. Here we have a carbon single bond oxygen carbon, and that is an ether. Is there anything else there? Probably there's another alcohol. Let's now go to look at heroin. Now heroin, interestingly, like cocaine, has got 2 ester groups. 1, 2 ester groups. Just like morphine, it has got an ether group. So these are 2 ester links there. It's got an ether group. There's a benzene ring. And again, just like morphine, heroin structure is very similar to morphine. It has got a tertiary amine group. Can we spot any more on these drugs? Yep, we have an alkene group here. If we now go on to our LSD molecule, you can see here that we have a nitrogen, so you might think, oh, that's an amine. However, when you see the nitrogen connected directly to a carbon double bond oxygen, it is not an amine, it is an amide. And can you see the nitrogen here has got 2 groups joined to it? So it's an N substituted amide. Here we have, this time this is an amine because it's not next to a carbon with a double bond oxygen, and again it's a tertiary amine. Here we have, again, this is a secondary amine. Why is it a secondary amine? Because it's joined to two other carbons. There's a benzene ring, here's an alkene group, and here we have another tertiary amine, and this looks like an alkene group here. Now let's look at THC, commonly known as cannabis. And cannabis doesn't have many functional groups. You can see here we have either alcohol and benzene. When they're joined together, that's called a phenol group, and that's or an alcohol group, and that's where the ol comes from. Tetrahydro, we can see here that there is an ether group